Good morning. Today, I'd like to talk about arrays in Fortran. In particular, I want to start basically from nothing and build up all the way into a polynomial interpolation program. The syntax to declare an array is data type. X value is going to be an ordinary double precision variable. This creates an array named X whose indexes are 0 through 50 inclusive. Likewise, F has indexes 0 through 50. I ask the user to enter n for the data set, then for each index value I, 0 to n, I read an x value and an f value, storing them into the corresponding positions in arrays x and f. Then, as always, we do a sanity check to make sure that what we've entered is what we think we've entered. At the moment, that's all we'll be doing. So let's say that n is 3. I'll put in some data points that are on the graph of y equal x squared. So when n is 3, these are our n plus 1 for data points. The information you entered, the n is 3, and the x and f numbers are as they should be. So we'll have a double precision function, lnk. Obviously, I need to send it n and k. I need to send it the value at which I want to evaluate lnk. I have to send it the x values. Strictly speaking, I don't really need to send it the f values. I'll send the result back in value of the Lagrange polynomial. Implicit none means that I have to declare everything. N and k are being sent to the functions. I will be my loop counter. As in the main program, I have to be careful to index the arrays the way that I want to refer to them. If you'll consult your notes, you'll see that this is exactly what we said we were going to do in order to calculate these Lagrange polynomials. At the moment, this doesn't do anything. I'm not using the lnk polynomials. I just want to make sure that this will compile. During our in-class discussion, we figured out that if you take one of the x's out of the interpolating data set and stick it into ln comma k of x, what you get is either 0 or 1. You get 0 if the index on the x is different from k, and you get 1 if they are the same. This is new in the main program. For each of the ln comma k of x polynomials, I'm going to print out a message that I'm looking into polynomial number k, then for each value 0 to n, the variable x value will be x number j. I'm going to evaluate L in k evaluated at x number j. I'm going to print out to the screen k, j, and the Lagrange polynomial value. When k and j are the same, I'm supposed to get 1, otherwise I'm supposed to get 0. Looking into polynomial number 0, these numbers are the value of k, and these numbers are the values of j. When k and j are both 0, I get 1, and otherwise I get 0, with the understanding that the computer has formatted it a little oddly. The negative of 0 is 0. Looking into polynomial 1, when k and j are both 1, I get 1 for an answer, and 0 otherwise. In polynomial 2, when k is 2 and j is 2, we get 1, and 0s otherwise. And likewise, the third one works out that way as well. This convinces me that the Lagrange polynomial part is working as it should be working. Just like we did with the Lagrange polynomials, I'm going to put in a function that will evaluate the interpolating polynomial. Initially, I'm just going to make sure that that routine compiles correctly, and then in the next program, we'll take a look at whether it's working or not. Double precision function p for interpolating polynomial. I have to send it the size of the problem, the double precision number that I want to evaluate the polynomial at, the data set. This time I really do need to send both x and f. I'll send the result back in a variable called p-value. Implicit none, integer n comma k, declaration of my arrays done in the same way that it was done in the other program units, and because p is going to make use of function lnk, I have to declare it as double precision because of the implicit none. This is a sum. Initially, we'll set the sum equal to 0, and then for each k value from 0 to n, we will increase p-value by an amount f number k times Lagrange polynomial number k evaluated at x value. We will add all of those things up. The result is the value of the Lagrange polynomial, as we've seen before. There's no point in running this because we're not actually doing anything with the p polynomial yet. We will do that in the next program, 5.f90. sanity check. For each value of x in my data set, I'm going to print out that x value. Also, I'm going to print out the difference between the function value from the data set and what comes out of the interpolating polynomial. If things are working correctly, that second column of numbers should all be 0, or 0 at least up to rounding errors. And as you can see, things are going our way. Lastly, we will take the preceding program and put one additional thing in. I'm going to ask the user for a variable called nplot. We will divide the range of x values up into nplot equally sized subintervals. For each endpoint of a subinterval, we will calculate the x value, we will calculate the value of the interpolating polynomial, and print them out to the screen. Read nplot. For I equals 0 to nplot inclusive, I'm going to let x value be x0 plus xn minus x0 divided by the double precision version of nplot times double precision version of I. I'm assuming that I typed the data set in so that the x's go from smallest to biggest. If that's not the case, there are ways around that. Print the x value and the value of interpolating polynomial p that goes with that x value. If I pick nplot to be 3, that should make the x values out of my interpolating data set. As you can see, the x values are 1, 2, 3, and 4, while the f values are, as they should be, 1, 4, 9, and 16. We already knew that that should happen, but it's good to check. If I run it again, and tell it instead of 3 subdivisions that I want 15, it very quickly calculates these numbers, the x values, the corresponding p of x numbers, and prints them to the screen. There are a couple of points of interest here. When the x value is 1, the p value is 1, as it should be. When the x value is 2, the p value is 4. When the x value is 3, the p value is 9. And when the x value is 4, the p number is 16. We already knew that that should happen, but what we didn't have were all these other x, p of x pairs. Another point of interest is numbers like this. These are rounding errors. We're going to have to talk about that in detail in the not too distant future, but at the moment it's enough to remember that a double precision variable in decimal, usually you say it has 15 or 16 digits of accuracy. If you see a number that's roughly 1 in size, and you see something unexpected in the 15th or 16th decimal place, you shouldn't regard that as being alarming in any way. I hope everybody has a good day. I'll talk to you again soon.